Hi everyone, I'm Sharuth and I'll be talking about our work titled Structuring Representation Geometry with Rotationally Equivariant Contrastive Learning, done jointly with my wonderful collaborators Joshua Robinson, Derek Lim, Soledad Villar, and Stephanie Egelka. Invariant self-supervised learning is based on this foundational principle that similar objects are to be mapped at similar embeddings in the representation space. Similar positives or objects are often created from the same image by applying a set of augmentations. However, researchers have been recently focusing on equivariant contrastive learning instead, where similar objects or transformations in the input space correspond to deterministic transformations in the embedding space, which are denoted by TA. This learns a richer representation which can be adapted to a range of downstream tasks and does not enforce such strong inductive biases of invariance to a given set of augmentations. In this work, we propose equivariant and a framework for equivariant contrastive learning, which we call as contrastive augmentation induced rotational equivariance or CARE. CARE is based on two key principles, with the first one saying that we want to map complex augmentations in the input space to simple linear transformations in the embedding space. Since the geometry in contrastive learning is typically a hypersphere, linear transformations on the hypersphere correspond to isometries or orthogonal transformations in the embedding space. So we call an embedding mapping F orthogonally equivariant if it learns this equivariance where TA corresponds to an orthogonal matrix. The second principle of equivariance is based on the idea that we want to become orthogonally equivariant merely by learning from pairs of points, so that approach is scalable, such as invariant contrastive learning. So we propose this approach which preserves the angle between pairs of points before and after augmentation. That is, we take inner product of the embeddings of two different points after augmentations and take its difference between the inner product of the embeddings before applying that particular augmentation. We also established theoretical guarantees for this particular framework, with the first one saying that if there exists such an orthogonal matrix Ra such that our mapping is actually orthogonal equivariant, in such a case our loss will be exactly minimized. The inverse of this statement also holds, where we can show that if this loss is exactly minimized to zero, then for almost every augmentation A, there will exist an orthogonal matrix R such that F is orthogonal equivariant to R. This result also holds for the finite sample loss as shown in the proposition 3. Moving forward, as a corollary of the result, we can show that when the loss is exactly minimized, then this mapping rho from an augmentation to the corresponding rotation and transformation in the embedding space enjoys consistency under compositions and actually forms a group homomorphism. These results also hold for inexact minimization of the loss and are shown in our paper. Our framework extends to other groups as well, such as the groups which are stabilizers of bilinear form, example the Lorentz groups with Minkowski inner product, which have applications in special relativity, and also the symplectic group, which is used to characterize the Hamiltonian dynamical systems. Our approach also extends to different geometries of embedding space, such as the hyperboloid model of hyperbolic spaces. Coming to some results, we first test whether CARE can actually learn the SO3 manifold, and to do so, we learn representations of proteins from the protein bank dataset. Here we show the embeddings correspond to different approaches when the initial protein molecule is rotated along one of the axes from 0 to 2 pi. If an approach is actually learning the SO3 manifold, it should trace a complete circle when rotated across each of these axes. And as shown here, CARE is actually able to do so, and none of the approaches, be it invariant or equivariant, such as equimod, can do this. So in this work, we proposed CARE, which learns equivariance and preserves the expressivity of the backbone architectures and is a very promising structure for Siamese networks because it's just based on pairs of points. Mapping complex transformations in the input space to simple transformations in the embedding space has a lot of nice properties and can generalize better to out of distribution tasks. Thank you so much for listening. Here's a link to a paper and to our code base. Thank you.